Thank you for this opportunity. So today I'll be talking about how to efficiently learn on device in spite of all the uncertainties that John was talking about. So in on-device learning, we take a pre-trained model from the cloud and then deploy it to the edge device. Then we keep on adapting or training the model on the device based on all the uncertain data or the new data that is available, while performing inferences as required. So there's a need to continuously adapt in uncertain conditions. Now, of course, learning at the edge brings in its share of benefits in terms of better model personalization, privacy preservation, and non-reliance on cloud that reduces power consumption. But there remain many challenges. The edge devices, as we all know, are limited in terms of compute, storage, and power, and really cannot cater to the demands of learning with backpropagation, that is the powerhouse of training today. Additionally, if the data becomes noisy or adversarial, the model will start mispredicting or overfitting and start producing garbage results. So today, I will focus on the backprop-related critical challenges that are the biggest hurdle to on-device learning. Now, closer look at backpropagation from a hardware viewpoint says that it requires a large memory footprint for gradient computations and storage, as well as large training time that will expend huge amount of energy. Furthermore, to achieve high and confident predictions, backpropagation needs high precision computations, which will further add to the storage and compute cost. These requirements are difficult to be met by resource-constrained edge devices such as your mobile phones, drones, etc., and thus present a huge challenge. Now, as John mentioned, these are certain things that are still under exploration. We still have to do a lot of work. And I'll be talking about some key techniques that we are looking at in order to address the backprop complexity for on-device learning. First, we are looking at model-aware learning, where we ask how to use the pre-trained model's information on the edge device to learn new data with less memory overhead. Second, data-aware learning, where we are taking a neuromorphic spiking network approach in order to learn based on input difficulty. And finally, hardware-aware learning, where we are asking how to implement the learning to improve the efficiency of hardware resource usage and thus reduce power consumption. Okay, so as part of the DARPA Shell program for the past 2 years, we have investigated model-aware learning and have made substantial improvements. Say we have a pre-trained model learned on animal dataset. Now, depending upon whether the on-device data is correlated or uncorrelated with the existing information, as you can see from these pictures here, we are going to dynamically adjust the amount of gradient computation that we do while keeping the weights of the model frozen. Now, this approach gives us more than 300% reduction in memory during training, while also reducing inference complexity by 200%. And this also maintains competitive accuracy compared to state-of-the-art solutions. Now, moving on, as part of the JUMP 2.0 program in the Caucasus Center, we have been investigating data-aware on-device learning. Here, the key idea is that all inputs are not the same. Say you want to recognize me, of course, when in the picture where I'm standing against a plain background is going to be much easier than when I'm in a crowd. Thus, instead of expending the same time and effort for both the images, it makes sense to dynamically adjust the training time required by the model based on the input difficulty. So we applied this approach on spiking neural networks and got remarkable results with more than 350% reduction in training latency per image at ISO or higher accuracy than state-of-the-art solutions. And the most interesting thing about this approach is that most real-world data sets that exist today do have this kind of variation in difficulty where the model can deem more than 70% of the inputs to be easy. So this method is going to be very effective for a large class of problems. Finally, as part of the DARPA YFA that I'm honored to be selected for, I'm exploring hardware awareness for on-device learning. And the key idea here is to perform co-exploration of neural network and underlying hardware architecture using a NAS technique or neural architecture search technique. So here the algorithm is going to reconfigure itself based on feedback from hardware statistics such as energy, latency, area. And the hardware will also reconfigure its own resources based on the accuracy requirements set by the algorithm. So in this case, there's a need to really think of the hardware-software stack development together, as Bill was mentioning. And we have started investigating this NAS approach on an emerging in-memory computing platform and have found that our approach of co-exploration performs more than 150% higher computations at 400% lower power consumption than any other state-of-the-art IMC accelerator that we know of. So to summarize, model-aware, data-aware, and hardware-aware learning techniques have individually demonstrated significant improvements in memory efficiency, reduced training time, as well as power consumption. Ultimately, the convergence of these approaches through algorithm hardware co-design that still remains a non-trivial challenge will unlock new possibilities for AI innovation and deployment of uncertain learning at the edge. Thank you.